Hello again. In this video, we're going to begin talking about the material from section 4.9, which is on antiderivatives. Now in calculus, there are two fundamental operations. One, of course, is the derivative, which we're very familiar with by now, but the other is known as the antiderivative. Okay, so here's the definition of the antiderivative. A function capital F is an antiderivative of small f on an interval I, provided that the derivative of capital F with respect to x is equal to small f of x for all x in the interval I. Okay, so let's go over some examples of antiderivatives so you can get a feel for how they work. Okay, so let's try to find the antiderivatives of 2x. Okay, so what we're trying to do is we're thinking backwards. When we're asking for the antiderivative of 2x, what we want to know is what function did we take the derivative of to get 2x? So we're kind of thinking backwards now, right? Opposite of what the derivative is. Okay, and of course, if you think about it, it would have had to have been x squared, right? The derivative of x squared is 2x. Notice I said, what are the antiderivatives of 2x? So that implies there's more than one. Of course there is, because why couldn't I say x squared plus 1? Right? The derivative of x squared plus 1 is also 2x, and that's because the derivative of 1 is actually equal to 0, because it's a constant. So for that matter, why couldn't I add any number to x squared? Right? X squared plus 3 would also be an antiderivative of 2x. So the way we write this in general is we say that there's a whole family of antiderivatives of 2x. And the way we write that is x squared plus any constant. We just use capital C for any constant. Okay, so there's actually an entire family of antiderivatives of 2x, and they look like this. X squared plus any constant. Okay, so let's try this one. What are the antiderivatives of 1 over 1 plus x squared? Now this one's a little harder. If you go back and look in chapter 3, when we talked about inverse trig functions, the derivative of inverse tangent of x happened to be 1 over 1 plus x squared. If you want the entire family, of course, you would have to add any constant to that. Okay. By the way, we usually reserve capital F of x to stand for the antiderivative of small f of x. So if we wrote this out in this kind of notation, we would call this capital F of x, since it's the family of antiderivatives for small f of x. Okay, so over here we would call this one capital F of x, since it's the antiderivatives for this function, which is small f of x. Okay, so that basically means that if you take the derivative of the capital F of x, you're always going to get small f of x. Right, so if you take the derivative of this capital F of x, right, you end up with the small f of x. Right, same here as well. Okay, so we usually reserve capital F of x to stand for the antiderivatives of small f of x. Okay, so let's look at this last one. So let's find the antiderivatives of cosine of x. Okay, so the derivative of some function equals cosine of x. What is that function? Well, if you think about it, it would have to have been sine of x. Right? The derivative of sine of x gives you cosine of x. And then if you add c to that, then that gives you the whole family of antiderivatives for cosine of x. Okay, so the whole family would look like that. Okay, so for now, the way we're going to find antiderivatives is by thinking backwards. We're going to try to figure out what function did we take the derivative of to get to this small f of x. Now in the future though, when we become more and more familiar with these antiderivatives, we have a table that you can refer to remind you of what they are. So for example, on a table, you might see this notation. This is called the antiderivative operator. It's a script S. Then at the very end of this, you have this dx, which is the differential change in x. And in between these two symbols, we put functions. And so what this means is we're finding the antiderivative of whatever the function is that appears between these two symbols. And this is known as the antiderivative operator. Now, you'll also see this referred to as a definite integral. Indefinite integral. Later on, we'll talk about definite integrals when we get to chapter 5. So there is a difference between an indefinite integral and a definite integral. An indefinite integral is essentially the same as an antiderivative. And this is our symbol for indefinite integrals or antiderivatives. So for example, if you wanted to find the antiderivative of sine of x, you would put that in between these two symbols. And so that's what this basically is asking us. What's the antiderivative of sine of x? And this refers to what it's with respect to. So this means it's with respect to x. In other words, x is the independent variable. This tells us what the independent variable is. Okay, and so of course the answer here, the antiderivative of cosine of x, okay, is sine of x plus any constant. So that's how we denote antiderivatives. Okay, so for this one, you would write it like this. So this means the antiderivatives of 1 over 1 plus x squared, and of course the answer is going to be inverse tangent of x plus a constant. Okay, and then this one up here you would write as the antiderivative of 2x with respect to x is x squared plus c. Actually, the antiderivatives of 2x would be x squared plus c. So we're going to start using this antiderivative operator symbol more and more. And again, you might see it referred to as an indefinite integral. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.